In this video, we will look at Stokes Theorem and Divergence Theorem, which are the final two theorems of vector analysis. Now, if we look here, we have three surfaces. In this first surface right here, we see that we have a single, simple closed curve as our boundary. In the middle surface, we see that we have three simple closed curves as our boundary. This is not three boundaries. This is one boundary that consists of three curves. And finally, in this surface here, there is no boundary, and so we call this a closed surface. Now, much like when you're dealing with the Green's theorem, when we looked at a curve and the boundary of a curve, if we're given a surface S, then the boundary of S will be represented as partial S. We now need to discuss the boundary orientation. So when S is oriented, we can specify an orientation of the boundary of S, which is called the boundary orientation. Imagine that you are a unit normal vector walking along the boundary curve with your head at the head end of the vector and your feet at the tail end. The boundary orientation is the direction for which the surface is on your left as you walk. As you can see here, your head is out here, it's an outward pointing normal, your feet are here. This would be the direction that the surface is on your left. We can now state Stokes' theorem. Let S be an oriented surface with parameterization. This should be a G from D to S, where D is the domain in the plane bounded by smooth, simple, closed curves, and G is one-to-one and regular, except possibly on the boundary of D. And let F be a vector field whose components have continuous partial derivatives on an open region containing S. Then the circulation along the boundary of S of F is equal to the surface integral of the curl of F. Now this is an extension of the circulation form of Green's theorems into 3 dimensions. To prove this, we're going to make the simplifying assumption that S is the graph of a function z equals f of xy lying over domain D in the xy plane. Furthermore, we can write the theorem as 3 separate equalities. This proof boils down to then proving that all 3 of these equalities hold. So if we can show that all 3 hold, then we have proven Stokes' theorem. We are only going to prove the first equality in this video. The remaining 2 will be left as an exercise. Orient S with an upward pointing normal, and let C be the boundary of S, be the boundary curve, with orientation determined by the orientation of S. Let C naught be the boundary of D in the xy plane, and let R naught of T equal x of t, y of t for A less than equal to T less than equal to B. This will be the parameterization for C naught. Now the boundary C projects onto C naught, and so C would have this parameterization right here. Thus we can write the circulation in this form. Now this integral is precisely the integral obtained by integrating f1 over the curve c naught in R2 with parameterization of R naught. So the circulation of C is actually the circulation of C naught of f1 xy f of xy dx. We can now apply Green's theorem to this. That'll give us this double integral right here. Now we can use chain rule to evaluate partial y of this. And so we can write the circulation as this integral right here. Now keep this integral in mind. On the other hand, S has this parameterization right here. Thus, we get an upward normal pointing vector here. So now the curl of f sub 1I, a value at g dot n, here is the curl. Here's n. When we do the dot product out, we wind up with this. So to evaluate surface integrals, remember the method we derived, we would get this double integral right here. And if you notice, this is the exact double integral we got with the circulation. So we can say the two integrals are equal, thus the equality holds, and the proof is complete. We will now go ahead and verify Stokes theorem for this vector field and the upper hemisphere of the unit sphere with outward pointing normal vectors. So I will go ahead and sketch out the surface and then return when I have a decent sketch. And I'm back. Now this is our surface S. What we can do is we're going to have normal vector pointing outward, so that'll look like that. With that in mind, this right here is going to be the boundary of S. Its orientation then, if we imagine we're walking, keep the surface on the left, so remember our feet are going to be on the actual curve itself, because that is where this is, and our head will be out here. So we're walking. To keep it on the left, we'd have to walk in this direction, and that is the counterclockwise direction. To verify Stokes theorem, there are two integrals we have to evaluate. We have to do the line integral, and we have to do the surface integral. Let us begin with the line integral. Now, the boundary of S is the unit circle, and as we know, this will have the following parameterization. Our theta is cosine theta, sine theta, 0, where theta will go from 0 to 2 pi. This means that r prime would be negative sine cosine 0. So our circulation across the boundary, or I should say along the boundary of S, of F, is now the surface integral. I'm sorry. I'm doing the line integral. Is now the integral from 0 to 2 pi, F evaluated at R, which is negative sine of theta, 2 cosine of theta, and then cosine of theta plus 0, dotted with R prime, which would be negative sine of theta, cosine of theta, 0, d theta. This is the integral from 0 to 2 pi of sine squared theta plus 2 cosine squared theta d theta. If we rewrite sine squared theta as 1 minus cosine squared theta, we'll be left with 1 plus cosine squared theta d theta. Using the reduction identity for cosine squared, we have 1 plus a half cosine 2 theta d theta. Now, we're integrating over 2 complete periods of cosine 2 theta, so that will wind up integrating out to 0. So effectively what we have is the integral from 0 to 2 pi of 3/2 d theta, and that'll wind up just being 3 pi. Now we look at the surface integral. Since we're dealing with the upper hemisphere of a unit sphere, our parameterization for the surface would be cosine of sine phi sine theta sine phi cosine phi. Now theta will still go from 0 to 2 pi, but now phi, because we're dealing with the upper hemisphere, is 0 to pi over 2. Now we need the curl of f. Now we do this curl out. Partial y of this is 0, partial z of that is 0, 0 minus 0. Then we get partial z of this is 0, and then minus 1. Then it'll be 2 minus negative 1, which is 3. Now we also know our normal vector. This was already derived. This is sine of phi times the parameterization of a unit sphere and so our surface integral of the curl of f becomes the double integral over our domain of curl of f dot with n. So it'll be sine of phi times 0 negative sine theta sine phi then plus 3 cosine of phi dA. Now, of course, we know what our domain is. All right, so the integral from 0 to 2 pi, integral from 0 to pi over 2. Distribute this sine of phi through. Negative sine theta sine squared phi plus 3 sine phi cosine phi d phi d theta. Since we're integrating over a period of sine theta, this will wind up going to 0. And so effectively what we have is the double integral 0 to 2 pi, 0 to pi over 2 of 3 sine phi cosine phi d phi d theta, which will be 2 pi times the integral from 0 to pi over 2, 3 sine phi cosine phi d phi. So we'll have 3 pi times sine squared of phi evaluated phi 0 to pi over 2, which is 3 pi. Therefore, we can conclude that the circulation along the boundary of f is equal to the surface integral of the curl of f, which is what we wanted to verify. And so we are finished. Now, with Stokes' theorem, we can find an interpretation for the curl Consider a plane through a point P with unit normal vector n. Let C be a small circle in the plane, centered at P and enclosing a region D. By Stokes' theorem, we'll have this. Now, if C is sufficiently small, then the curl of f would approximately be the curl of f evaluated at P. And so the double integral here would become this dot product. Now, let's look at this dot product. That would be the norm of the curl times cosine of theta, where theta is the angle between that curl and the unit normal n. Thus, we can write both of these statements right here. What this tells us is that the curl encodes the circulation per unit area in every plane P in a simple way, as this dot product, right? So that's what this first statement was telling us. Now, the second statement tells us that the circulation rate is directly related to the cosine of the angle between the curl and that unit normal vector. And now we can look at the divergence theorem. Let S be a closed surface that encloses a region W in R3. That is, the surface is equal to the boundary of W. Assume that S is piecewise smooth and is oriented by normal vectors pointing to the outside of W. If F is a vector field whose components have continuous partial derivatives in an open domain containing W, then the surface integral of S is the triple integral of the triple integral along W of the divergence of F. As before, we shall make the simplifying assumption W is a rectangular box. Furthermore, we will write the theorem as three equalities. Just with Stokes' theorem and Green's theorem, the proof boils down to showing that all of these equalities hold. If we can do that, then we have proven the theorem. Just as with Stokes' theorem, we will only prove the first equality in this video. The remaining two will then be left as an exercise. Now, the surface integral over the boundary of W is the sum of the integrals over the six faces of S. However, since f1 hat is orthogonal to the normal vectors of the top, bottom, and two sides, the surface integrals over these faces is 0. This means that the only contributions to the surface integral come from the front and back faces, denoted as f sub f and f sub b, respectively. Thus, the surface integral along the boundary of W is the surface integral along the front plus the surface integral along the back. We will use these parameterizations for the front and the back. So for the front, we use byz. For the back, we use ayz. And both have the exact same normal vector of I hat. However, if you notice, the orientation of the back is opposite that of the front. So when we go and actually write this out, we go to write these out using the orientations or the parameterizations, this will be minus. Right? So this is the front and this is the back. Now we can combine those into a single double integral. And notice that this piece right here is a fundamental theorem of calculus application. Right? We can write that as this integral right here. However, this piece right here is the divergence. Is this divergence here? So we can now write this triple integral, which is, remember, the surface integral, as the triple integral of the divergence. That is the equality that we wanted to show, and so the proof is complete. We now wish to go ahead and verify the divergence theorem for this vector field and the closed cylinder given right here, where both x and y are between -2 and 2, and z is between 0 and 5. Once again, I will go ahead and sketch this surface out, and then return once I have it. So here's our surface. Now this region right in here is our domain D. Of course, then that whole thing is the surface W. Now, we're going to be using outward pointing normal vectors. So that means down here, we're going to have a normal vector pointing that way. This is negative k hat. Up here we have one pointing up there. That is positive k hat. And of course, we're going to have normal vectors along the sides like so. Once again, this is going to boil down to evaluating two integrals, the surface integral and the triple integral. Let us begin by evaluating the surface integral. There are three surfaces we have to consider. The top, up here, the bottom, and then let's call it the side of the cylinder, right? This whole thing here. We will evaluate each of these three individually, starting with the top. We will use this parameterization here, g of t. Right, so we're looking here. Well, this is a circle. Right, so our parameterization, we're going to have x and y, right? But z is fixed. So x, y, z is fixed at 5. And the domain is a disk. So let's write it this way. Now, if we look, we need the normal vector. It's going to be partial x, so 1, 0, 0, crossed with partial y. This will give us, as expected, k hat, 0, 0, 1. Therefore, the surface integral of the top of f becomes this double integral. Of f of g, so y, 5y, 25, dotted with 0, 0, 1, dA. Now what this becomes is the double integral in d of just 25 dA. If we factor out the 25, we're left with the double integral dA, which is just the area of the domain. Now the domain was a disk of radius 4. I'm sorry, of radius 2. So we get 1 pi for the surface integral of the top. For the bottom, we'll use parameterization GB. Now again, if we look, x and y can change, but z is fixed at 0. So x, y, 0. And again, the domain is the disk of radius 4. Then we need to calculate n. Well, again, n will be the same thing. Except we have to remember it is now oriented downwards. So we're going to have this negative. If we look at now the double integral of SB, so the surface integral along the bottom, this becomes double integral over d, f of g, which is y, 0, 0, dotted with 0, 0, 1. Well, that just winds up being 0 dA. And so we have no flux through the bottom. This just now leaves the side. Now, if we look at the side, this is a classic cylinder. Classic cylinder of radius 2 and height 5. Now, the parameterization of a cylinder of radius r was r cosine theta, so it would be 2 cosine theta, 2 sine theta, and then z. The domain 0 less than or equal to theta less than 2 pi, and 0 less than or equal to z less than or equal to 5. The normal vector, if you recall, will be 2 cosine theta, 2 sine theta, 0. Thus, the surface integral through the side of f, double integral over d, f of g, 2 sine theta, 2z sine theta, and then z squared, dotted with n, dA. This is the double integral over d of 4 sine theta cosine theta plus 4z sine squared theta dA. Let me rewrite that z. There we go. But the domain was for theta 0 to 2 pi and for z 0 to 5. 0 to 2 pi, 0 to 5. We're integrating over a complete period. That first term will then just integrate out to 0. And so we are effectively left with this. If we rewrite sine squared of theta as 1/2 minus 1/2 cosine of 2 theta, then we see that once again we're integrating over this time 2 cycles. So that cosine of 2 theta is going to integrate out to 0, and again effectively what we are left with is 2 pi times the integral from 0 to 5 of 2z dz. This will then become 2 pi z squared for z 0 to 5, which is 50 pi. So the total surface integral of f through s is the surface integral through the front minus the surface integral through the back plus the surface integral through the sides, and we wind up with 150 pi. Right, now all we have to do is show that the triple integral over w gives us the same thing. All right, so we can w in cylindrical coordinates as 0 less than equal to r less than equal to 2, 0 less than equal to theta less than 2 pi, and 0 less than equal to z less than or equal to 5. Now we just need divergence of f. Right, so divergence of y, yz, z squared. This will be 0 plus z plus 2z, which is just 3z. So our triple integral over w of the divergence of f becomes the triple integral over w of 3z. Now write this in cylindrical, 0 to 2 pi, 0 to 2, 0 to 5, of 3rz dz dr d theta, which is 2 pi, integral 0 to 2, integral 0 to 5, of 3rz dz dr. This will be 2 pi times the integral from 0 to 2, 3rz squared over 2, as z goes from 0 to 5. Factor out that 3 halves, we'll be left with 3 pi, integral from 0 to 2, 25r. This is 75 pi over 2 times r squared. R goes from 0 to 2. That becomes 75 pi times 2, which is 150 pi. And so what we have just shown is that this surface integral is equal to this triple integral, which is what we wanted to show. And so the verification is complete. Now with the divergence theorem, we can find an interpretation for divergence. If we assume that F is the velocity field of a fluid, then the flux of F through a surface S is the flow rate, right? That is, it's the volume of fluid passing through S per unit time. If S encloses a region W, then the flux is the surface integral, which is this triple integral by divergence theorem. Now assume that S is a small sphere centered at a point P. Because the divergence is continuous, we can approximate it on W by a constant value, divergence of F evaluated at a point P, specifically at the center. Then the flux will become the divergence of f at P times the volume of W, which means that the divergence of f at P is approximately the flux over the volume of W. What this says is that the divergence is approximately the flow rate across a small sphere divided by the volume of the sphere. This becomes more exact as the sphere shrinks. So the divergence of f at P has an interpretation as outward flow rate of f per unit volume near P. And we have three cases. The divergence is positive, in which case there is a net outflow of fluid across any small closed surface enclosing P. And we can think of this as a net creation of fluid. So for this case, we call P a source. The divergence could be negative. Then there is a net outflow of fluid across any small closed surface enclosing P. We can think of this as a net destruction of fluid. So for this case, we call P a sink. Or the divergence could be zero, in which case the net flow across any small closed surface enclosing P is approximately zero. A vector field where the divergence is zero everywhere is said to be incompressible. And that concludes this video on Stokes and divergence theorem, and it also happens to conclude this video series on calculus 3.